Yeah. Okay. So, just a quick announcement. So, after this talk will be lunch. Before we eat lunch, I want everyone to go down to the bottom. We're going to take a group picture. Okay. And tomorrow, you're going to get a surprise. With that, right? All right, so thanks to Brandon for coming. So Brandon is currently at Hopkins. He was a student here working with myself and Brian. So he's going to talk to us about making giant crystals.
Thank you. So as JP said, so currently I'm a postdoc at Johns Hopkins University. I was an alumnus here. I graduated. So I defended mid-February 2020, so right before COVID happened. So this is like my first talk after emerging from 2 years of being stuck in the dark recesses of labs in different facilities. But first, I'd like to thank, so as JP said, I'm an alumnus here, so I'd like to thank the two groups that I worked in here. So the top group is Dr. Rodriguez's lab here, and the bottom group, these were, I think, both taken in 2019 or so. JP's group here, and then currently, as I said, I'm at Johns Hopkins University. I'm a postdoc with Dr. Tyrell McQueen. And I'd like to thank also two of my collaborators that I met here at UMD, who are now at other facilities who I work with a lot. Dr. Shishlin Joe at Argonne National Lab and Dr. Dan Campbell at Lawrence Livermore National Lab. So what I'm going to be talking about today is hydrothermal synthesis in terms of how you might use it to make things that you might be interested in for quantum materials. But really, the hydrothermal synthesis that started, in terms of us thinking about how hydrothermal synthesis will be used for making new materials, is the hydrothermal vents in nature. So this is an example of what a hydrothermal vent might look like in nature. So the first one actually wasn't discovered until 1977, and it was found through seabed mapping off the Galapagos Islands. And even though this picture here looks like it's the sky, this is actually just the water, so this is the seabed. And what happens in these environments is you have seawater infiltration around nearby volcanic activity, and the seawater comes in, and again, this is seabed. It's really deep in most places, so the water temperature is very cold, so it's about 2C water here. It infiltrates through, this earth crust infiltration. It gets close to these magma chambers that are, again, this is areas where there is nearby volcanic activity, and because this groundwater infiltration doesn't allow for water to boil off, it starts to build up at very high pressure, and then it gets released at some, hydrothermal vent that is nearby. And in these hydrothermal vents is where you start to have these different chemical reactions with, whatever constituents you might have in the groundwater or the seawater in terms of minerals or anything like that might be dissolved, and you start to make these new compounds. So on the left here there's two main classes of hydrothermal vents. One's called a black smoker, so you can see it as black smoke, usually are sulfur containing, and then white smokers. And then these are, again, these were found, 1977 is not that old, but these are found relatively new in terms of mapping out where currently there's a lot of work going into trying to map out exactly where all these hydrothermal vents are in nature. Another aspect of hydrothermal research that is not related to quantum materials exactly, but I find in terms of looking at this literature, I found really interesting was people interested in these hydrothermal vents in terms of the origin of life on the Earth. So basically, during one of these explorations in 1979, after the first hydrothermal vent was found, trying to map and find more of these hydrothermal vents, one of these marine microbiologists, came to the thought or the conclusion that these are very deep. These environments are very, very deep underwater. So these are, and of course, they did find microbial life nearby these. Well, not only microbial life, but also macro life in terms of snails and crabs and things like that. So this little cartoon here where a crab is living near the hydrothermal vent. And it came to this realization that these are regions where you have microbial life or life forming where there's not sun or energy from the sun being put into the system. So you can have, this is a possibility for where, building blocks for life may have originated on Earth. So there's two more recent Nature Chemistry papers trying to actually model exactly how this would have happened by taking, you know, the fundamental building blocks of, you know, what would be in these hydrothermal vents and trying to actually show that they can be, you can work them up all the way to very complex things like RNA or different proteins. So in terms of crystal growth, I can pretty much definitively say that the best crystals are grown hydrothermally. So you all laughed when Dr. Lin mentioned a 0.4 kilogram crystal that was measured. So obviously, it's kind of hard to get a scale, but you see these little, these aren't little people, like little miniature people. These are real people in these hydrothermal caves where these extremely large single crystals of gypsum have been formed over millions of years, obviously. So obviously, we don't have millions of years to wait for crystals for our measurements. But you can see that, you know, nature is the best crystal grower, and you know, we cannot pretty much in the lab cannot compete on this kind of length scale. But this is just to give you an idea of how nice the crystal you can grow hydrothermal. So this is a more down to earth, well, excuse the pun. Less down to earth, I would say, it's not, you know, made in earth, but actual growing crystals for device usage and actually growing them in the lab. So this is an example of trying to grow quartz at 2 different facilities. So the quartz was used during, well, the main boom for quartz was during World War I and World War II, or World War II, I think, for growing quartz for different devices. So this is a quartz growing hydrothermal autoclave here at Bell Labs, and this is the world's largest quartz growing autoclave in Japan. So basically, all of these little things, these little crystals you see here, are about, you know, hand size or so, are single crystals of quartz that are grown using these hydrothermal. So this hydrothermal reactor, well, both of these are in the ground, and they use these cranes to lift out these seed crystals here for growing quartz single crystals. So here's a basic outline of my talk. So I'm going to talk about the basics of hydrothermal synthesis, the physical chemistry of hydrothermal synthesis, and most importantly, phase diagrams. So I know you guys had a talk on Monday about binary and ternary phase diagrams for something like flux growth or solid state growth. So I'll show you things that are relatively similar to that for hydrothermal synthesis. I'll talk about autoclaves, so the things if you've had the practicals and hydrothermals, things you probably have already seen already, but to give you an idea of if you wanted to get into hydrothermal synthesis, the things you need in the lab. And then, you know, a brief application to quantum materials and some of the research I did here when I was at the University of Maryland using hydrothermal reactors. So talk about the basics of hydrothermal. So what is hydrothermal? There's a couple definitions that you might see in the literature, but mainly the commonly accepted definition is this last one you see here, which is a synthesis or reaction in aqueous media above 100 C, so above the boiling point of water, and above 1 atmospheric pressure. So it's in a closed system, and since you're going above the boiling point of water, you build up some autogeneous pressure, and that gets you above 1 atmospheric pressure inside whatever your reactor is. So if you're reading in the hydrothermal literature or in literature about these techniques, you might see another term that's floated around called solvothermal. Solvothermal is essentially a catch-all term. That's basically everything that's hydrothermal, except you're not using water as a solvent. You're using some other solvent. And that can be a number of things, which I'll talk about later. But it's pretty much a catch-all for things like ethylene glycol, you know, glycerin, that sort of thing. And then another term that is used kind of with different definitions is mineralizers, but the best definition I can give you for mineralizers when it's mentioned in literature now is pretty much any compound or constituent that's added to a reaction that will help in either modulate the dissolution of whatever you're trying to make, or in the dielectric or the viscosity of whatever you're trying to, other solvent to help dissolve whatever you're trying to make. So most of the times if you see a mineralizer it's used to help modulate the dissolution of whether it's your starting materials or your products to, you know, help expedite your reaction in some sort of way. So a little bit about the historical development of hydrothermal synthesis, and, you know, kind of bring it into what we're thinking about today. So the first big breakthrough in hydrothermal synthesis was in 1845, where they were trying to grow these insoluble oxides in water. And what they found most of the time was that by increasing the pH, well, multiple things, by increasing the pH of your solution, but also increasing the temperature and pressure, you could actually help dissolve these insoluble oxides such as ruby, emerald, sapphire, quartz, and dissolve them in solution and then help grow larger single crystals from solution. And then skip a couple of these older ones and bring you into more recent times. So in the 1990s, there was a big kind of, due to the increase in experimental capabilities, an attempt to do in situ diffraction of hydrothermal synthesis. So a lot of times when someone talks about hydrothermal synthesis, they'll call it this black box reaction. Basically, you put everything in the autoclave, or you put everything in the liner, put everything in the autoclave, seal it up, put it in the oven, forget about it, pull it out, see what happens. But you have no idea what's happening in between. As mentioned before, a lot of the things that are done, because this is relatively low temperature, is a lot of kinetically stable phases. And for a lot of these systems, because it's this black box reaction, we don't know exactly how the kinetics works to form the phases we want. So in the 1990s, there was a big push for this in situ diffraction to kind of understand all the intermediates that are being formed along the reaction scheme and try to understand exactly what leads to the formation of these kinetically stable phases. In 2000s, there was obviously a ton of work on the preparation of metal organic frameworks using hydrothermal. So a lot of the hydrothermal literature you see now is trying to synthesize some of these metal organic frameworks and zeolites as well. And then more recently, in 2010s, with computational power and theory really increasing, there's a big push for this. I mean, I think this is all in all of material science, and generally speaking, but for hydrothermal synthesis as well. And I'll show you one slide on this later. Is this first principles predicted hydrothermal synthesis, and trying to make, what I'll show you these phase diagrams later, make multi-component phase diagrams, and then combine that with DFT to try to find exactly what phase you're going to make at different pH values or different pressure values and that sort of stuff. And I'll show you a slide on that later. So what are some advantages of hydrothermal versus a high temperature synthesis that we've gone over so far this week, like solid state, self-flux, flux reaction, CVT, or something like that. So the big two ones that I bolded are the big ones. Because most hydrothermal, especially the hydrothermal that I mentioned today, is pretty low temperature. So most of the hydrothermal that I've done, between my work at Hopkins and here is all below 200 C. So very low temperature relative to, say, a flux growth up to 1100 C or so. Is that metastable phases are available. Because you're at very low temperatures, you can make some metastable states that you're not a victim to just thermodynamics running away with whatever reaction you want. Another big takeaway in terms of, things you might not be interested in or worried about as grad students, but you might be later on in your career, is it's a pretty low energy process, which means it's cheaper. The hydrothermal autoclaves you can get from the manufacturer are pretty cheap. And because you don't need to go to very high temperatures, you don't need to buy a high temperature furnace, you can just get a pretty standard convection oven, and that's all you need to heat up your autoclave. So all the things you need to do hydrothermal synthesis is pretty cheap. And then what kind of materials can be prepared? This is just a short list, but a lot of things, again, targeting metastable phases or something like that of any of these, this list of compounds here. So why do we use water, and why is hydrothermal synthesis kind of focused around water? So water, as you probably heard from Gen Chem or something like that, maybe is the ultimate solvent. It can pretty much be used for most things. It can solubilize most things. So this is just a chart, like a reference table for you to keep in mind about the properties of water at high temperature and at room temperature. You can see, so at room temperature, it has a pretty high viscosity. Its dielectric constant is obviously pretty large, again, because it's polar. So it'll be used to help dissolve things that are polar. And its density is near unity, right? But you can see as we start to increase the temperature, so what you might do in hydrothermal synthesis, for example, you can see the viscosity goes down really low, which might be useful in crystal growth. The dielectric constant start to approach unity. So at higher temperatures, you can start to dissolve things that might not be necessarily polar or might not dissolve in water at room temperature, and the density goes way down to it. So water can help, in terms of solving, depending on what you are worried about dissolving, at different temperatures, you can kind of span that whole region. And the important thing is that the solvent you use is what helps mediate the crystal growth. So there's two things that mainly help mediate your crystal growth, which is the viscosity, which I showed you how water changes viscosity with respect to temperature, and the dielectric constant, because the dielectric constant determines what's going to be actually soluble in your system. So this is just a plot of zinc oxide crystals being formed hydrothermally at different temperatures, and in different pressures. So the pressure got cut off there. Oh no, it's up here, sorry. And you can see that you have different structures or different morphologies being formed in different regimes. And that's all because of the fact that water has a different dielectric constant and different viscosity at those different temperatures. So this is just some quick pointers about remembering that tuning, this is something that you would most likely get into later on down the line in terms of optimizing the crystal growth. Is actually optimizing the viscosity of your solvent or the dielectric constant of your solvent to make sure that you are growing optimal crystals for your system. Some other solvents that you might see in literature with their dielectric constants and boiling points listed. So again, the important thing about hydrothermal too is that because, or not just hydrothermal, but solvent, to get above 1 bar of autogenous pressure, you need to go above the boiling point of whatever solvent you have. So if you're using DMSO, for example, you need to go above 189 to have an autogenous pressure of more than 1 atmosphere. And the dielectric constants, again, these are all labeled or at room temperature, but they would change with respect to maybe not as drastically as water, but they would change at different temperatures. But these are some different solvents that you might see in the literature listed for solvent thermal synthesis. So is hydrothermal a high pressure technique? So definitely it is at some temperature regimes and different things called filling fraction. I'll show you what that means. But for most of the syntheses that I did at the University of Maryland, I'm doing here, or doing it at Johns Hopkins, I was stuck, not stuck, but I mostly did all my syntheses below 200 C. So you can see the autogenous pressure is very, very low. So not necessarily a high pressure technique. But you can see that these percentages here are what's called the filling fraction. It's basically what fraction of the closed container are you filling up. And you can see that once you start to get to high filling fractions or very high temperatures or a combination of both, your pressure can increase very, very fast. So this is to help your design experiments in terms of, if you think you need very, very high pressure to form the phase you want, but also for safety considerations. You don't want to put a 90% filled autoclave that can only hold 400 bar of pressure at 300 C, and you'll have a little bit of an explosion or something bad happen in the lab. So the essentials, so if you had the practical so far, you will have seen all these different pieces. So this is the different pieces of a standard hydrothermal autoclave. So you have the autoclave, which is this gray thing. Most of the time, the ones you'll see in the lab when you do the practicals, or if you've done them already, is basically just a stainless steel container. Very, very simple, and that basically holds your liner. So then you also have your liner, which is this white thing. I'll show a list of what different liners you can use depending on what different reagents you might have. But most liners that you will use at low temperatures are things that are usually completely inert to whatever your reagents are. So most of the time for these low temperature things, it's something like Teflon, so a Teflon liner. And then inside you have your mineralizer, which is your solvent plus whatever you might add to help tune your dielectric constant and your viscosity to help dissolve your nutrient, which is basically all the things that your reagents that you want to dissolve or help in your reaction for your products. And then for much more sophisticated syntheses, for example, the ones I showed you with the quartz crystals coming out of that large vessel, you'll have seed crystals which might be in a different region of your autoclave. And these seed crystals are basically just to help seed your crystal growth, and you grow larger crystals from that seed crystal. But in most of the time, when you're doing something with a seed crystal, you need to have a temperature gradient to actually tune, to have, basically you have dissolution. You would have dissolution in this regime and growth in this regime, and you would tune your pressure or your temperature in those different regimes to have, the two different things being met. So thermodynamic principles. So the physical chemistry of hydrothermal, generally speaking, is still a very active field of research, not just in crystal growth, but also in the things I mentioned before. So in like geochemical literature in terms of hydrothermal vents and things like that. One thing I didn't mention before is hydrothermal synthesis and hydrothermal, I guess classification is a really big topic in geochemical literature as well. So you'll find if you're interested in hydrothermal synthesis, that a lot of the things you might be searching for will be in geochemical journals and geochemical literature because they're very interested in this field as well. The studies of crystal growth during hydrothermal conditions, as I mentioned, really started to take off with with the use of like synchrotron X-rays or in situ neutron diffraction, things like that. And you can actually, try to study the kinetics of crystal growth using hydrothermal. So this is an experiment that we helped design at 17 PM at Argonne National Lab, where we actually have a quartz tube filled with water and our reagents, and I'll show you more about this later. And we actually measure, we take diffraction patterns every 30 seconds, and we can plot, after we do refill refinement, we can plot the different constituents of a reaction and the products and the reagents over time and see exactly the kinetics of what these metastable states are being formed as a function of time. So this was done over, more than 1,000 minutes. So this was done, this was a long-term scan on the X-ray system. So I'll get into physical chemistry of hydrothermal synthesis, and I'll mostly talk about phase diagrams, the things that, if you're interested in hydrothermal synthesis, the things you will reference or should reference to kind of get an understanding of the things you might want to make. So again, hydrothermal synthesis is kind of noted as this black box because there's so many factors that you might need to change in a reaction with different products. So in flux growth, you might have, you might change the flux, you might change the temperature, and you might, depending on what stoichiometry you're trying to find, that's not even you can't even really change the stoichiometry that too much because you're trying to target some exact compound or some exact phase. But in hydrothermal synthesis, there are a lot of little knobs that we can turn. Pressure, temperature, pH, oxidation potential, whether it's intrinsic or external. The concentration of each component that you add is a knob that you can turn, and there's a bunch of other ones. But again, so if you're a grad student and you're trying to make something, you don't want to be having to do one reaction at 120C, one reaction at 125C, and then you start multiplying that by all the different knobs that you have to turn. You can see how you can be stuck in the lab for a very, very long time. So the next couple slides with phase diagrams and thinking about the different things that help guide your syntheses will be pretty useful for that. But the most important phase diagram, I would say, is this one I showed earlier in terms of pressure and temperature. And this tells you essentially the pressure that you will build up in your system, autogeneous from again, this is just for water at the different filling fractions to make sure that in terms of a safety consideration, you don't have anything too drastic happen in your lab. So your PI is not matter. So the second most important phase diagram that you'll see when you're trying to think about hydrothermal synthesis is what's called Courbet diagrams. And Courbet diagrams are pretty much akin to ternary or binary or ternary phase diagrams that you would see for a solid state growth or a flux growth. And what you have in these plots is it's a function, it's your electrochemical potential as a function of pH. And this is all calculated for water. And basically it tells you the different species of whatever single element you have will be at what species you'll have at that single element in solution at these different regimes. So if you're, like, for example, if you are targeting, Fe3 plus, and you need that as your product, you're going to need to be in this regime in terms of your electrochemical potential in your pH phase space. And I'll get into, a little bit more in depth about this now. So if you haven't had chemistry for a while, I haven't thought about electrochemistry, this will be a little bit of a review. The entire Courbet diagram is computed from electrochemical values, essentially. So, if you remember your electrochemical series, this is just a filler figure to remind you of what the muscle memory of what the electrochemical series might look like. But basically, the key pointers too is that every Courbet diagram that you'll see, like listed in a table or in a reference manual, is all calculated based on the oxidation potential of that element at standard temperature and pressure. Which again, for hydrothermal, because we're not at standard temperature and pressure, is not exactly ideal. But for some elements, they have been calculated with higher temperatures as well. Mostly, there are elements that are like in the geochemical literature where they're prevalent in the Earth's crust, for example, like aluminum, iron, and that sort of stuff. But you can find them, for example, for iron, you can find a Courbet diagram all the way up to 400 degrees C if you need that. Okay, so a little bit of review about electrochemistry before I show you how a Courbet diagram is manufactured. So again, all the Courbet diagrams are based on electrochemistry. So if you consider you have some element A and it's going to oxidize, it has some electrochemical potential at SCP, which is this EA number or whatever. And that has some Gibbs free energy associated with the oxidation. And you can write your Gibbs free energy with respect to that electrochemical potential, or you can write it with respect to your equilibrium constant, depending on what the reaction you have. And in general, that the electrochemical potential at any non-standard temperature and pressure, or non-basic, I should say that, not basic, but basic could be pH. And not, so your electrochemical potential at some time that's not, depending on your reaction, is based on your reaction quotient. So this is at non-equilibrium state, essentially. So you have, your starting material and your products, and you have some reaction quotient relative to not being at equilibrium. So again, important to realize and note that Courbet diagrams are only useful. So another problem in terms of thinking about Courbet diagrams generally is that they're only based on the thermodynamics of the system and thermodynamic quantities. But so it doesn't factor in kinetics at all. So if you're worried about, or if you're thinking about trying to stabilize a metastable state based on kinetics, the Courbet diagrams can only give you so much information about guiding your statistics. And again, the Courbet diagrams are only considered using water. So if you were to expand out this reaction quotient with water as one of the constituents, you can actually simplify, or not, I guess it's not simple, more simple, but it's simple relative to water, is that you basically have your electrochemical potential is a function of your concentration and your pH. So that's essentially how the Courbet diagrams are arranged. So all the Courbet diagrams I'll show you, or the construction of one I'll show you next, is all based on plotting electrochemical potential as a function of pH, but you'll see the electrochemical potential is also a function of concentration. So all Courbet diagrams actually have 3 axes, but almost all the Courbet diagrams you'll see in literature is just electrochemical potential versus pH. If you're worried, or if you start doing a synthesis and you think that concentration might be playing a very large role in your synthesis, then there are some, you can find in literature the Courbet diagrams plotted for all 3 dimensions at once. So how do you construct a Courbet diagram? So again, it's electrochemical potential as a function of pH. And because this is only one slice in that 3-dimensional concentration plot, most Courbet diagrams take a concentration of 10 to the minus 6 molar, which for most of your systems might not necessarily be the case. But if you start to be worried again, if you start to be worried about concentration playing a large role, you can start to include that 3rd dimension. So most Courbet diagrams, you'll see 2 dotted lines on them in the background, and those 2 dotted lines tell you something about the solvent you're using, so water. So basically, you have 2 half-cell reactions that you can have with water. So above the blue line, you have water being oxidized so that you have oxygen in equilibrium with water in the solution. In between these 2 regimes, you have water is stable. Below this regime, you have water being reduced to hydrogen gas in equilibrium with water. So that shows you, again, the 2 different regimes you have. So, for example, if you have a system where you have a constituent, let's say iron 3+ or something like that, that is above the water being stable range, you have to think about what you're going to use to oxidize your system, because you need to oxidize water as well to get all the way up to, say, iron 3+ or something like that. So now we're going to look at actually constructing the Courbet diagram for an element. This is a relatively simple Courbet diagram, so this is the Courbet diagram for zinc. So it basically has 4 lines, and each one of those lines is electrochemical potential versus pH, essentially. And you see, this is because in solution, zinc has 4 stable states, depending on the pH or the electrochemical potential. So we can have zinc 2+, we can have zinc hydroxide, we can have hydrogen HZnO2-, and we can have ZnO2-. And each one of those, depending on the half-cell reaction you have, has its own electrochemical potential. This is basically Y equals mx plus b, or electrochemical potential versus pH. So they basically all have their own slopes. And basically what these tell you is that below this electrochemical potential, for example, this first reaction, you'll have zinc zinc 2+ being reduced to zinc. So below the red line, you'll have zinc metal. Same thing with the orange line. Below the orange line, you have zinc metal. Below the green line, you have zinc metal. And below the blue line, you have zinc metal. So what does that tell you? It tells you that below all those lines, you have zinc being completely immune. So if you have enough reducing environment, you put your zinc in the water, it won't do anything. But above all those lines, depending on what the different lines were, you'll have different constituents that are stable. So above the red line in this pH region, you'll have Zn2+, and in this region, you have zinc hydroxide. In this pH region, you have HZnO2-, HZnO2, minus. And in this region, you have ZnO2, 2 minus. And again, that's all computed from the Nernst equation, which I showed you before. I didn't name it, but it's called the Nernst equation if you haven't seen it in a long time. But basically, yeah, this tells you the different regions that are stable. And then, depending on, essentially in the regions you see here, you have essentially a pH acid-base problem, essentially. So for example, in the equilibrium line here between Zn2 plus and Zn and zinc hydroxide, you essentially just have an acid-base problem. And then you can go back to the Nernst equation and actually figure out where the equilibrium between those two species will be based on this, reducing the Nernst equation here. And you can find that if you do all the calculations based on the Gibbs free energy of, say this reaction here, you can find that the Zn2 plus and zinc hydroxide will be the equilibrium at pH 8.5. And you can actually construct these Courbet diagrams from, first principles if you want to. But again, all these Courbet diagrams for all the elements are computed and tabulated in different handbooks and things like that. But importantly, what you might see in literature, especially in the geochemical literature, is this distinction between immunity and corrosion. So for zinc, for example, all these red regions are species where the species that is considered, for example, Zn2 plus or HZnO2 minus is soluble in water. So all these red regions is areas where you might have what you might see the term as corrosion. So if you put zinc into water at these different regions, your zinc will start to be corroded and will be dissolved in solution. In the blue region I mentioned before, it's zinc metal, completely unreacted, so that's what's called the immunity region. But in terms of the geochemical literature, things you might see as well is this green region, zinc hydroxide, is what's called passivation region. So zinc hydroxide is soluble in water, but it will form in solution. So if you put in a chunk of zinc metal, zinc hydroxide will form on the surface. The zinc hydroxide on the surface is not soluble in water, so your zinc metal piece that you put in will be passivated against further corrosion. So again, in terms of quantum materials, it might not be too useful, but if you look, it's useful for thinking about the geochemical literature or things that you might, or terminology you might see in the literature. So let's look at some Courbet diagrams for which you probably have some general understanding of, or some conceptual understanding of what might happen. Because the zinc one, is a little bit abstract, and the iron one again. The iron one, you should have some conceptualization in terms of iron turning to rust and things like that. But gold's Courbet diagram, you should have a pretty good understanding. So if you put a piece of gold into water, will it dissolve? Will it corrode? I sure hope not, or else, every time it rains, people would be running inside out faster than they already did if they're wearing jewelry. But you can see here that in the stable region of water, gold has immunity. So gold will not dissolve in water. Another example is copper. So if you think about Statue of Liberty is copper, right? But is the Statue of Liberty copper colored now? No. And the reason for that is in the stable region of water, you had all these different copper species that are available depending on the pH. So if you have acid rain, or maybe you have somehow you have basic rain or something like that, you have all these different species that the copper on the surface can convert to. And that's why, for example, the Statue of Liberty has all this patina, what's called patina, from basically the corrosion and the passivation of the different copper constituents on the surface of the Statue of Liberty. Some other phase diagrams you'll see, one that you might see in older literature, not used too much now, is called an NC diagram. And basically what it is the ratio of two of the chemical components of whatever solution you're trying to make, and percent of mineralizer and water. So the mineralizer in this situation, the system was sodium hydroxide, so sodium hydroxide, which is helping with the dissolution and the formation of the products. And the N is a ratio of zirconium oxide and silicon oxide. And basically what they do in these systems is they plot the different species that are being formed in these different phase space. And that way you have a much more predictive understanding. If you wanted to exactly make this phase, you have to be in this concentration regime. So this is essentially, the NC diagram is essentially the concentration analog of the Courbet diagram without considering electrochemical potential at all. The one reason these aren't used too much today, or you don't see them as much today, is because they require a lot of trial and error. I mean, not necessarily trial and error, but they require a lot of experimentation, because you need to actually do all of these, you need to find, do points at all of these different regions to find what phases are being formed. So one thing I mentioned previously, which was in this push for predictive materials design using DFT and ab initio methods. So this is a very recent paper in Chemistry of Materials last year. So basically what they were trying to do here is combine multi-element Courbet diagrams. So most of the Courbet diagrams you'll see in literature are just for one element, like the ones I showed you, like gold or iron. So combine multi-element Courbet diagrams and computed compound stability using DFT or other techniques, and actually predict at different regions in your electrochemical potential versus pH phase space exactly what phases are going to form from multi-element Courbet diagram. So this is an example of Courbet or multi-element Courbet diagram combining DFT for bismuth, copper, oxyselenide. So that so you can see all these different. And again, this is just one cut in concentration space, but they predict all these different species that you'll have, not only in solution but solid insoluble species you'll have in the reaction. So if you're targeting, for example, you're targeting bismuth, copper, oxyselenide, you should be in this general region of pH electrochemical phase space if you want to make these different compounds. So this paper is much more of a proof of concept. So they show these multi-element Courbet diagrams for a bunch of different mixtures of elements. But you can imagine doing this for all the different combinations of elements at all the different concentrations. It becomes a very large computational problem to do all of that. But it's something I think they're pushing for as a possibility for helping, guide material synthesis from a computational point of view. So again, I mentioned the kinetics of crystal growth. This is one of the reasons that hydrothermal synthesis, is dubbed as black box reaction. Is you put everything in, you put it in the oven, forget about it until you have to go collect it, take it out. You have no idea what happens in between. If we're trying to synthesize metastable states, what actually happens in between is really interesting for us because we want to know how we can use that kinetic pathway to maybe form other compounds. So again, this is just an example, a more detailed example of doing that in situ X-ray diffraction at 17 BM, where we actually have all the different patterns. And you can kind of see here, you have different peaks that are only showing up at a function of these are all just different scans as a function of time increasing. And once we do the refill refinement, we can see our iron concentration is going down, our lithium hydroxide, this is a lithium hydroxide intercalated iron selenide, that phase is increasing, and we also have some lithium carbonate impurity that does start to form, but then kind of levels off. So it gives us an idea, once you have this sort of data, you can go a little bit more in depth and kind of think about the kinetics of how your compounds are actually being formed. So get into autoclaves. So this is a quick reference table that you can use if you're interested in doing hydrothermal synthesis in the lab. The two main types of the ones you'll see if you haven't done the practical yet are these hard type stainless steel and nickel body and flat plate autoclaves. So basically they have a very, very high pressure, 400 bar is like the upper limit. And the temperature again is, so the par type isn't necessarily limited to 250, but the 250 limit is based on the liner, which I'll talk about a little bit. But you can also do hydrothermal synthesis in quartz tubes. So this is like the cheapest bootstrap version of doing hydrothermal synthesis. The problem is that quartz tubes are, they're not as pressure resistant. So if you were going to do, hydrothermal synthesis in quartz tubes, you're limited to about 6 bar of pressure. So you really need to think about that filling fraction, the temperature you're getting to, and what kind of autogeneous pressure you have in your system. So I was trying to do some of this while I was here in Maryland, and I can tell you I burst a ton of tubes. So you have to be careful in thinking about your engineering controls and things like that. But if you do need to go to really high temperatures and really high pressures, this cold cone steel Tuttle-Roy type, which I'll show you too, which we have one in the lab here at QMD, can get you to those very high pressures and very high temperatures. The last consideration you need to think about with your autoclaves is your liner. So the liner is what's holding all your reagents. So the stainless steel, like whatever you're using here, is just other than the quartz tube. The quartz tube is also holding. It doesn't necessarily have to, but it can. Your liner is what's holding all your reagents. So you need to have something that's completely inert to the whatever your system is. So for example, Teflon is pretty much the most commonly used. It's pretty inert to chlorides and hydroxides and pretty strong acids as well. The problem with Teflon is it starts to deform. I think this 300 is a little bit ambitious. It starts to deform at about 250 C. And when you start to have the liner deform in your autoclave, it starts to not be able to hold pressure. And if you're not holding pressure, you're no longer doing hydrothermal synthesis, and all your water will evaporate off. So 250 is, I would say, a pretty good limit for hydrothermal synthesis using Teflon. If you do need to go to higher temperatures, or if you need to use different environments, you can use these different metals, so titanium, silver, platinum, gold. Again, the big problem there is cost. If you need to be using a platinum crucible that can hold 100 milligrams of sample or 100 milliliters of liquid, it's not going to be cheap. So it's something you need to consider. So this is, for those who haven't had a practical, this is what a PAR autoclave looks like. So basically, you have your stainless steel shell and all the different components, your Teflon liner, and basically it's as simple as it looks. You put all your stuff into the liner, you put the liner in the stainless steel body, you put on these are what's called corrosion discs. They're just to make sure that if there is anything that leaks out, it doesn't come in contact with the other constituents first. And this is what's called it's essentially a very cheap pressure relief valve, where it's basically just a pretty rigid spring against these two plates. So if you start to build up too much pressure inside, it will compress the spring and release pressure, so you don't have a catastrophic failure. And then this is just a screw lid that has a little like hex wrench notch there that you can really crank down using a torquing wrench or something like that. And then this is a picture of the total cold cone autoclave that if you did need to go to very, very high temperatures or pressures, you could use. It's a little bit more sophisticated and it's much more expertly machined in terms of the different components, because it can hold very high pressures. But this is an example of a Tuttle type furnace. I mean, a furnace using Tuttle type. So you can see our version. So this is the top here. This is the bottom here. So this furnace here, as you can see here, is very old. But basically, what it is it's a two-zone furnace for the hydrothermal autoclave to sit in, and we can control the temperature in the two different regions of this furnace to do a seeded crystal growth if you needed to. And this is an example of how much the filling fraction, as the phase diagram I showed you in the beginning, how much pressure you start to build up as you change the filling fraction. So this blue line is 50% filling of one of these autoclaves, and you can see even up to 600, we're only up about like 5,000 psi. But if we go up to 75 at the same temperature, we're about 15,000 psi. The pressure starts to increase, pretty fast as you start to increase the temperature. And if you had like 90% filling, it would be much more, straight up and down here. So some quick applications to, quantum materials in the work I did here. So I've been mentioning and I've been talking about this idea of kinetically stable states and metastability. So just to give you a brief, conceptualization of what that means. So basically, any metastable state is any local minimum in your energy landscape. So if you have, your energy landscape with respect to, pressure and temperature or whatever else, whatever other, driving forces you have all these local minimum, which might be kinetically stable phases. But if you're using, a traditional solid state method where you go to very high temperatures, you're always going to go over this energy barrier and go into your stable state. That's pretty much always going to be the case. But if you're at the, maybe the perfectly correct pressure and temperature regime, you might be able to, stay stuck in one of these kinetically stable states, one of these metastable states. An example is, different allotropes of carbon. So Buckminster fullerene is a metastable state. Diamond is technically a metastable state. Luckily for everyone who has diamond jewelry, its lifetime it's in terms of conversion to graphite is on the age of the universe, so you don't have to worry about that, actually being a problem. But graphite is actually the stable state of carbon. So everything, is going to be going to carbon or graphite if you give it enough time. So one of the things I was interested in when I was here was trying to make the sulfur analog of iron, the simplest iron-based superconductor, iron selenide. So iron selenide is a 8-covalent superconductor, but the sulfide analog is not a thermodynamically stable phase. So I know you saw binary phase diagrams on Monday, but if you're looking at the binary phase diagram for iron and sulfur, the layered, so I haven't showed you the layered structure yet, the layered iron sulfide structure, which is isostructural with iron selenide, does not exist on this phase diagram, this thermodynamic phase diagram. So if you wanted to make it, you might have to start thinking about it being a metastable state and actually using kinetics. So this is the layered analog to iron selenide. So we wanted to see if there was a way to make this to see if it is a superconductor as well. So basically, we can do exactly that. We can find the correct pressure and temperature conditions to actually stay stuck in one of these local minima and form, this layered iron sulfide. So in the geochemical literature, there's actually a bunch of methods to do this. So these are two, somewhat old 1990s and 1964 literature to actually make, because it's a naturally occurring mineral, iron sulfide in the structure called Mackinaw. And these are different routes to get polycrystalline Mackinaw from, this isn't even hydrothermal. This is just at room temperature. We can do these reactions to get Mackinaw. But we've also found that you can also do this hydrothermally. So you can mix iron. You can do sodium sulfide as your sulfur source, but we also use thiourea. You add sodium hydroxide as a mineralizer, and that also increases the pH to 14. If your temperature is relatively low, so below 150, because then you get 150, you start to form other phases. So let's say 120 is a good temperature. You can form, polycrystalline single phase Mackinaw pretty easily. But in terms of actually, doing let's say we wanted to measure resistivity, we wanted to make single crystals, we wanted to see if there was another way to do this. Another way to do this is actually take a related compound, which is potassium. Essentially, it's potassium intercalated iron sulfide. So it's basically the same layer structure, but in between the layers is potassium ions. And you can actually, single crystals of this is a thermodynamically stable phase. And you can take single crystals of this compound, which you can make from a self-flux reaction of potassium, iron, and sulfur. And you can take these single crystals and actually turn them into this layered iron sulfide just by removing the potassium ion between the layers. And this can be done, again, hydrothermally with pretty much the same conditions as so this is what we call a bottom-up synthesis. We're making iron sulfur from the bottom up from the constituents. And this is what we might call a top-down synthesis, where we're taking the building block iron sulfide that has the right layers from this compound and basically converting it into the target compound in one. And we can actually turn, I'm not sure exactly if this is the exact crystal turned into this one. I'm pretty sure it is, I don't want to say exactly, but this is the type of single crystal conversion we can do with hydrothermal synthesis, for example. With that, I'd like to say thank you. So these are some references. Obviously the FQM textbook. This textbook here, the Handbook of Hydrothermal Technology, is a very, very good reference material as well. And these are two review articles on hydrothermal synthesis and synthetic chemistry essentially. So with that, I'll take any questions. Okay. Yes.
I have two questions. Is there any way to quench your hydrothermal product?
Yeah. So basically, the one thing I didn't mention is, I think I mentioned it in passing, but I didn't show a slide on, was basically you to get temperature of, to increase the temperature of your hydrothermal autoclave, you actually put it in an oven, essentially. And you can use the oven to do, depending on what ovens you have, obviously, you can do quenching by taking it out and putting it in, essentially air to fast quench or water if you need to, because it's essentially a closed system, so you can quench it that way. But you can also do crystal growth as you would do traditional from a solid state. You can program the furnace or the oven to cool at a slow rate as well, depending on how your crystallization works, which again, one of those black box problems you might not exactly know, but if you do slow cool your autoclave, that might be another method to make single crystal.
And another question is, do you know the stability of the hydrates at the dilution fridge temperature?
Say that again?
Do you know the stability of the hydrate bonds at the dilution fridge temperature?
No, that's a good question. Yeah, I'm not sure. Yeah.
So it sounds like from the beginning of your talk, you want everything to dissolve in your water. But are there cases where you might say you put in the 3 or 4 initial reagents and one of them stays a solid, and then you kind of have a mix between hydrothermal and solid state where the extra ions kind of diffuse into whatever stays a solid? Is there a particular point that you would want that to happen?
Generally speaking, yes. So there is a large body of literature where they actually use, I don't know what you would call it, I can't remember the term they actually use, where it's like a mixture of hydrothermal and flux, where they use like molten hydroxide fluxes, but hydroxides absorb a lot of water naturally. So you're actually doing a combination of hydrothermal and flux growth at the same time. So that's sort of what you're mentioning. But another thing that meant to touch on what you asked is putting something into your solution that will stay a solid, that won't, like you can, we've done examples of this where you put something in solution, it stays a solid and it doesn't react, and it doesn't participate in the reaction at all. So one example of that is we put in like a piece of tin in the hydrothermal reaction because that helps modulate the electrochemical potential of the system, and that actually doesn't participate in the reaction at all, but it helps us modulate things that would help crystal growth or the synthesis itself. Does that make sense? So kind of both. You can do both. One thing, if you're interested in the combination of flux and hydrothermal, the molten hydroxide work is really, really interesting.
Down here.
So you change the electrochemical potential by changing the ratio between the components, right?
Not necessarily. It depends also. So there are experiments or setups where you can actually apply an external voltage. Yeah, that can be done as well. Yeah.
So you can have a seed crystal with
Yes.
an electrode or
Yes, yeah, that's definitely done. The other thing you can do is, depending on, you can use different starting materials that have intrinsic, for example, like let's say you use a really strong oxidizing agent, like potassium permanganate. You use that as your manganese source, and that's going to help tune your electrochemical potential of your system, essentially. So it's just something you need to consider when you're developing or thinking about your reaction scheme, essentially.
What's sort of the state of like morphological control in? Because I know, for example, in solvent-thermal reactions, you can introduce modulators that will sort of create anyways, crystal morphology control.
Yeah, I would say, I mean, the slide I showed on the zinc oxide sort of, it depends on, and that's much more of the like the nanoscale people like, interested in that kind of morphological control, and then it gets down to not only tuning the pH, well the pH and the temperature and pressure because you're tuning the viscosity of water or whatever your solvent is, but then also kind of as you mentioned, introducing other things that might strictly help, like surfactants, for example, strictly help in terms of morphological control. So yeah, it's definitely for those who are interested in exact nanostructures of whatever you're making. There's definitely literature that people are doing that kind of research.
You have some examples of materials you grew where you had to really crank up the temperature and pressure, or you use this high pressure?
No, so I think, well, let's see how far back it was. Yeah, this system, I think, so two other grad students that are in the Franz lab, Stephanie, who, I'm not sure if they'll be here or they're around, Stephanie and Tim, they actually do use this. They're using it for, phosphate, so lithium phosphate, that sort of stuff. So in those systems, they do have to go up for most of the stuff that I was interested in. It's all below 200. But yeah, if they're around, they might have some perspective on that.
I have a question here. So, would it be possible to control just the pressure and maintaining all the other factors also? Like, is it possible to just, I don't know, work with different springs, for example? Like,
well, you can also, so if you remember about the pressure, let's see if I can pull it up far back. Yeah, this one. If you think about the pressure versus temperature, if you wanted to keep temperature constant, but you wanted to achieve a certain pressure, you could tune your filling level to be exactly what you might need to achieve that pressure. That makes sense? Because essentially, between 90% and 10% filling, you have all these different lines that would, be 85% filling, which might be to a different pressure at some specific temperature.
But normally there's no need to control mechanical pressure.
Not necessarily.
Is there systems where you do change the pressure?
What do you mean? I'm sure there are, yeah, in terms of, definitely in terms of morphological control, I've seen it. In terms of like people trying to make nanorods versus nanospheres, actually tuning that pressure, using the filling fraction essentially. But most of the time, like the research that I'm doing is, I would say, exploratory synthesis sort of stuff. So you're not getting that in depth. Remember, there's all these different knobs that you can control. you know, you're trying to tune the easier knobs first, and then worry about things that might be more useful for, you know, high quality crystal growth or something like that.
Is there any way to get temperature gradients, and would that even be a useful tool?
Yeah, for sure.
There's
So
already like 6 variables you have to.
yeah, no, the temperature gradient is, so this furnace I showed, a high temperature one. This is actually a 2-zone furnace, so there's one set of heating zone here and one at the bottom. And the benefit of that is, let's say you have something like quartz, which you have seed, well, also the figure I showed before about seed crystals. You basically set up a zone where all your constituents will dissolve. And then you have another zone at some temperature where the quartz will start to fall out of the solution, depending on the chemical potential or whatever you're tuning. So basically in those 2 zones, you have dissolution. It's essentially the same sort of thing as CVT. You have dissolution in one zone, it transports to the other zone based on convection. And then as it goes to the other zone, it falls out of solution, deposits on the crystal when you get slow crystal growth. So yeah, that's how they, essentially that picture I showed of those really large quartz crystals, that's how they grow.
From the 4-bay diagram,
Mhm.
you'd be able to know whether a metal will oxidize and then this oxidize will pass to the surface, or if it'll be sensitive to air and oxidize completely, I guess.
Yeah, I mean, most 4-bay diagrams I do mention, I mean, the thing you have to be worried about, like for example, the zinc hydroxide I showed, you just know that zinc hydroxide is insoluble in water, so it's going to passivate essentially. So yeah, essentially that kind of, that's how you would have to look at the different species that are in the different regions and see if they're soluble in water. Because most, unless you're looking in the geochemical literature specifically, they won't mention the terms corrosion or passivation. But if you are worried, let's say you want to have if you specifically want to have an oxide layer or whatever you're, you know, whatever you're considering, then you would want to be in a region where you have passivation.
Great, any other questions?
I have another, but I can't later.
Okay.
So the 2-component 4-bay diagrams that you showed, one that was calculated by DFT. Is it always just calculated by DFT? I know that.
No, so my understanding what they do is it's strictly just a multi-component 4-bay diagram, which is only calculated from like the Nernst equation, very simple. And then what they do is they do DFT computations on the different phases that are present in that ternary or quaternary system, and see, okay, let's see what the stability are for those different constituents at the different regions. And then they say, okay, the building blocks in terms of like bismuth 2+, copper 2+, O2- are all at this different pH and electrochemical region. It should form, this is the most stable, you know, bismuth, oxy, copper, selenide there. It should form that necessary. But again, it's all based on thermodynamics. So at low temperature and, you know, kinetics, there's some phases that might not necessarily form.
So you didn't need DFT, for example, for your iron sulfide?
No. That's all strictly Nernst equation, very simple electrochemistry, essentially.
Okay, thank you, Brendan. Okay, so it's lunchtime, but remember, first we're going to take a picture, so please congregate down in the bottom.